In this video, we're going to use a triple integral to calculate some probabilities when we have a joint probability distribution on three random variables. So we have the random variables x, y, z. We have the joint density function given to us by f of x, y, z equals some constant times e to the negative 0.5x plus 0.2y plus 0.1z if x and y and z are all positive and it's 0 otherwise. So the first thing we need to do is calculate the value of c. We remember that to be a joint probability distribution function, when we do our integral over the support, we have to get 1. So in this case, we integrate over the region that we're talking about, the e. When we integrate that joint density function, we have to get a 1. Well, the x, y, and z are all going off to infinity, so we write this as the improper integral basically 3 times. It's an improper triple integral, if you will, in this case. And the order doesn't matter because all of these are just constants. We don't have variables describing the region in terms of each other. Since we have constants everywhere, we can break up our integral into 3 pieces as 3 individual improper integrals. We could handle the improper integrals by doing limits of each one. We find an antiderivative for each of these. They all look similar. They just have different constants that we're multiplying the variables by. Plug in our endpoints and then take our limits. The limits of each of these pieces are going to be 0, so we'll get 2 times 5 times 10 when we do this integral, each of the 3 integrals I mean, and then take their limits. So we get 100 on the left-hand side, so we get 100c equals 1, so our c has to equal 1 over 100. And now we can use this function to help us calculate probabilities. If we want the probability that x is less than or equal to 1 and y is less than or equal to 1, well, that's giving us our bounds for our x and our bounds for our y. We don't have any bounds for our z other than what we defined the joint density function on, so that's still 0 to infinity. Again, we don't have any variables written in terms of other variables to bound our integrals here, so I can break this apart into 3 pieces just like we did in the previous example, and we can still handle that third integral as an improper integral by taking a limit, do our respective antiderivatives, and plug in our endpoints. And for some reason I didn't delete off the extra pieces here. This vertical bar shouldn't be here, and these shouldn't be here anymore because I already plugged them in there. And then this limit will turn out to be 10. So when we take the 10 times the 100th, you'll get a 1/10 here. You can factor a 2 out of the 2 terms here. You can factor a 5 out of the 2 terms here. So though it will cancel, all of that will end up canceling this 1/10 out in front after, again, when I move this 10 to the front. So that's why we just get 1 minus e to the negative 0.5 times 1 minus e to the negative 0.2. Now for the third part, where we want all 3 variables to be less than or equal to 1, this is set up very much like the previous example. Again, break it up into 3 integrals since we don't have any variables written in terms of any of the other ones. Take our antiderivatives, plug in our endpoints, and ignore the typos. Again, that's just a copy and paste from the previous one where I forgot to delete those things. And just like in the previous example, the previous part, I can factor out a 2 here, a 5 here, and a 10 here. That multiplies together to be 100. It'll cancel out the 100th, which is why we get 1 minus e to the negative 0.5 times 1 minus e to the negative 0.2 times 1 minus e to the negative 0.1 is our final answer.